Okay, so we're going to talk about boosting. And so boosting is a classifier or a way to make classifiers that has been very, very successful. It's done quite well in terms of both in terms of accuracy and in predictive power. So it doesn't does maybe have some problems with overfitting sometimes, but they can be alleviated. We will see how we can do that in the second half. So there are two kinds of boosting that we're going to look at here. And one is adaptive boosting, also called ADA boost. I think that's actually trademarked. And the idea of this is to build up a classifier from some very simple classifiers. So boosting is basically taking a whole bunch of very simple classifiers and then combine them somehow to get a very strong classifier. So in ADA boost, they're built on trees, but we're looking at the simplest possible tree you can have, namely a tree with just two nodes. So it's just one split, and the so in for such a tree, well, what is the decision boundary? Decision boundary will just be a hyperplane parallel to one of the coordinate planes. On 2 dimensions, it'll just be the decision boundary will just be a line that's parallel to either the x or the y-axis. So such a classifier just divides the data space into 2 half spaces. So there's no fancy stuff going on. So a weak classifier is one who's is classifying just slightly better than 50%. So its accuracy is just slightly better than 50%. So the idea of boosting is to sequentially apply these weak classifiers and then combine them along the way to get a much stronger classifier. And so in ADA boost, what we're getting is these GMs here are all tree stumps. They're all trees with just one split. And so what you do is you combine them using some coefficients that we have to compute. And then the predictor we end up with, a classifier we end up with, is just a sine of this. So this is, so ADA boost works for binary classifiers. So combines all these weak classifiers, put them together in a certain way that we have to talk about, and then it simply classifies them by the sign of this. Is the x here, does it give a plus or a minus? So those are the two choices. That's how we classify points. So the way the ADA boost works is that we look at our training set, and every time we apply such a weak classifier, some points will be correctly classified and some will be misclassified. And what we're going to do is we're going to apply weights to the data. So each data point is going to get a weight, and if the data point is misclassified by the classifier, the weak classified GM minus 1, then next it'll get a higher weight such that it'll have a better chance of being correctly classified by the next one. And we'll see exactly how this works. And so the data set is weighted. At the beginning, we just weighted with every point has the same weight. So we can, if we have 10 points, we give them all the weight 1/10. But that will change as we apply our classifiers. So for a weighted data set, we can define the weighted error of the classifier GM, and that's simply we sum over all the weights that are wrongly classified and divide by the sum of all the weights. Now I'm going to always make sure that my weights add up to 1, so I don't have to divide by this. So in that case, the weighted error of this classifier is just the sum of all the weights belonging to points that are misclassified. So so what we're trying to do is when we fit this classifier, we're trying to minimize this weighted error. So if we take a different classifier here, well, we're going to get a different weighted error. The weights are given now, but we can try different of these weak classifiers and find the one that gives us the lowest weighted error. So
can I ask one question, please?
Please.
So you said that to the data points which are misclassified,
yeah,
the next classifier they are given higher weight, right?
Yeah, exactly. Right.
But even in the next classifier, all the data points are being considered, correct?
Yeah, all the data points are being at each step, all the data points are being considered. Right.
So the data point which was previously correctly classified in GM-1 can get incorrectly classified, though it's with a lower weight in.
Yes, but it's not. We're not just applying this classifier GM. I mean, this GM is going to be added. It's going to get some coefficient, and then it's going to be added to a sum of these classifiers. So GM is not the new classifier. It's gonna be added to the sum of it. So the classifier, the final classifier is going to look like this, right? So it's going to be a sum of the weak classifiers with some coefficients in front of it. And so neither of these GMs here will do a very good job of classifying, but the sum of them, the weighted sum of them will classify very well. So we have to figure out different things. We have to figure out which alpha m's here should we choose, and how do we update the weights every time. So the update process works in this way. We put beta m equal to 1/2 times the log of this. This is called the odds. So 1 minus the error divided by the error. We take the log of this and multiply it by 1/2, and then the update is given by the new weight is taking the old weight and then multiplying by the exponential of 2 beta m times the 1 if the GM misclassifies the point, and 0 if it correctly classifies it. So you can see if it correctly classifies it, then this is 0. And that means that, in fact, the new WI is the same as the old one. So if this is, if GM classifies XI correctly, then this will be 0, and so WI is not changed. If it misclassifies it, then WI is going to be multiplied by X of 2 beta m. And here's the classifier. Then after m steps, the eta boost classifies and given by the sum of these things here, and we have to take the sign of it. I forgot to write that because it's actually the sign of this. So that's how we construct a classifier. So here's the here's the sort of the specifics. So let's consider a data set and labels plus or minus 1. So again, AdaBoost works in a binary for a binary classifier. And suppose we have some classifier, and then we're going to define a different loss function than what we have seen so far. It's called we define the exponential loss function. And we define it this way here. So gxi is going to be positive or negative. And so if g, it's actually going to be plus or minus 1. So if g correctly classifies x, so if this has the same sign as yi is plus or minus 1. If it correctly classifies it, what do we have then? Then we have that this is equal to this. So that means that the product here is positive. There's a minus in front of it. That means it's negative. So if we have correct classification, this is positive. And so x minus this will be less than 1.
Neil, shouldn't that be sign of gxi?
Here?
Yeah.
No, I mean, if it correctly classifies it, that means that this is positive, right?
Yes. So gxi will return some number that is either positive or negative, right? The sign will lose the magnitude and just keep the sign.
Yeah, right.
So if you want the exponential to be plus minus 1, it has to be sign of gxi, right?
Well, I don't care whether it's plus or minus 1. I just care that the exponent here, that if it's correctly classified, so if g of x has the same sign as
y,
as yi, then this will be less than 1. If it classifies it wrong, so they have opposite sign, well then yi times gxi will be negative, and then there's a minus in front of it. That'll make it positive. So that'll give us x of something positive which will be bigger than 1.
Mm-hmm.
So you can see that for those the terms in this sum here, those that are correctly classified, they will contribute something that's less than 1, while those that are misclassified, they'll contribute something bigger than 1. So it's not going to be 0, right? It's never going to be 0, but the more of these that are correctly classified, the smaller it'll be. So it does qualify as a loss function. It'll.
So the magnitude of whatever g is returning is also important here, right? When I choose a function.
Yeah, I mean it's not. I mean this you could say that this would be, for instance, it could be a linear function. This could be w dot xi, for instance.
Mm-hmm.
That would be something that's classifying, and then you would just say whether this is positive or negative.
Right.
Yeah.
Just one thing, that like gxi vj is a classifier. It will only classify as plus 1 or y given the data vector xi. The output.
Well, the classifier, right, is the sign of gx.
Yeah. So there's a
gx could be, for instance, a linear function, and then you would see is the value of this linear function, is that on xi, is that positive or negative? If it's positive, it has the same value as what? Yeah, sorry.
The thing that's plus or minus 1, you have to take the sign.
Yeah,
if
exactly.
you use the sign function, you'll get some magnitude floating around. Yeah.
Right. But we don't really care about that. We only care about whether the exponent there to the exponential, whether it's positive or negative.
You're trying to reason that the correctly classified ones lower the loss function, right? The loss function is smaller.
That's right. It does. Yeah, right. The more correctly classified points, so the more so suppose our g is given by just the dot product with some fixed vector w. Then what we're trying to find is the w such that as many of these dot products have the same sign as the label.
Yeah.
Is it clear?
Yeah, yeah.
Okay. So we want to construct a classifier of this form here. So again, the g is the function, and the thing that has values plus or minus 1 is the sign of this. So each gk here is some very simple classifier, and in this case, it's like a tree stump, so just a tree with two branches, so there's just one split. And so we're going to construct these things step by step. And so let's assume we have constructed.
So Niels, just a quick question. That beta that you showed a little bit earlier was a very carefully chosen function. It was log 1 minus,
right.
1 minus a.
Yes.
Can we just spend a moment just staring at that function and the choice of that specific update process?
Yeah, it will become clear as we go along. It's not. As it looks now, it looks like it's just been sort of grabbed out of the thing.
No, it looks like it's been cleverly chosen. I was just trying to understand the logic.
Indeed it has, but it's been chosen from some considerations that we will get to later. Okay. In fact, it does come from the fact that we are using this particular loss function here. So this is not a loss function we have seen before. This is the fact we're using this loss function is what's going to give us all these expressions for the betas. So we're going to construct these GJs, these tree stumps, or what we're choosing by step. So let's assume we have done a number of steps. We have constructed some classifier, little f, and we now want to update that to a classifier of this form, f plus beta of g, where g is a tree stump. So for a tree stump, right, then the actual value is plus or minus 1, because that's just a dividing it in 2. So it says send some x's to plus 1 and some x's to minus 1. So it's just going to have 2 values. So again, if we look at the loss function, this exponential loss function for the new classifier here, so that'll be of this form here, right? So our new classifier is this, and so our loss is given by this expression here. We just plug in this new classifier here. And so let's put the weight wi equal to the exponential of this part here. So this is sort of the local loss functions for the old classifier here. So let's put those equal to wi. And so we can then rewrite the loss function this way here. It's now the wi. If you take you have a sum, you have an exponential of a sum here, that's a product of the exponential. So it's a product of the exponential here, which is wi times the exponential of minus yji times this thing here. So we have the loss function can be written in this way here. So we get this weighted sum of these exponentials. So if you look at a particular one of these exponentials here, so it's like this. So both gxi and yji, so yji here is the label for xi in our data set or our training set. So they're both either plus or minus 1. So this exponential here is just going to be x of minus beta if the xi lies on the right side of this tree. So this decision boundary for this tree is just a line. It just divides the space into 2 half spaces. So if the xi lies on the correct side of it, then this is going to be yji times gxi is going to be 1. If it lies on the wrong side, so if it's on the wrong side of the railroad tracks, then this will be minus, then yji times gxi will be -1, and so it'll be x of beta here. So we can write it in this form. These exponentials are only going to take two values, x of plus beta or x of minus beta. And it's going to be x of minus beta when this g here correctly classifies xi, and it's going to be x of beta when it misclassifies it. So we can simply write our loss function this way here. It's x of minus beta times the sum of all the weights of the correctly classified ones plus x of beta times the sum of the weights of the incorrect or the wrongly classified ones. And so we can rewrite this, so I can subtract I can add and subtract so I add here x of minus beta times the sum of those that are incorrectly, forget it, those that are incorrectly classified and then I can subtract it again. And when I do this, all that happens is that I can take these x of minus beta and x of x of minus beta times the sum of all the, so I get from this plus this, I get x for minus beta times the sum of all the weights, and then I have a minus x for minus beta over the correctly classified ones, or the incorrectly classified ones, and I can put that up here. So I get this expression. This is just some arithmetic manipulation of this expression here. It's just we will need to be able to solve here. Of course, we want to find beta here, right? That's what we need. So let's again take the weighted error. So again, that's the sum over all the weights that are of the xi's that are misclassified divided by the sum of all the weights. And what I want to do is to minimize this expression here, right? This is so I'm simply taking this expression here and dividing it by the sum of all the weights. You see that gives me, if I divide this expression here by the sum of all the weights, this is going to cancel here, and here I'm just going to get the sum of the weights or the misclassified one divided by all the weights. That's the weighted error. So if I divide through by all the weights, I'm going to get this expression here, and this is what I want to minimize. So I want to find g that minimizes this. I want to find beta, and I want to find g that minimizes this. So first, to minimize with respect to beta, I just differentiate and put the derivative equal to 0. So if I do that, take this expression here, differentiate with respect to beta, I get this equation here. And you can see now that this gives me that if I solve this equation for beta, that gives me precisely this value for beta. So there's how that beta came around. So that's simply what we get, the beta that minimizes this this expression. So this expression here is the exponential loss function. So what we get by adding this term beta times g, then we should take a beta equal to this this expression here. So now I want a positive beta, and to have beta positive, I need that exp beta is bigger than exp minus beta. So exp beta minus exp minus beta is positive. So if I want to minimize, so this is what for a given error, for a given weighted error, gives me the minimum of this function here. And now I want to minimize. So I find a beta given by this. I want to minimize the whole expression here, and that means that, and because this is positive, that means that the one that minimizes this is the one that gives me the smallest weighted error here. So the beta and the weighted error that gives me the minimum is given by this beta, and then the minimum error I can get. So from G, I want to take the G that gives me the smallest weighted error. So that means we have all the ingredients to extend our classifier. We have the beta, and we choose the tree stump that minimizes the weighted error. That will give us the smallest exponential error function. So the updated classifier is going to be this. We got the beta, and we choose the G to minimize the weighted error. Then the new weights are going to be this, right? The old weights were these, and now the new weights are we're adding this beta times GM to our classifiers. We get another classifier. We get a different classifier, namely this one. And the new weights are then Wi times x for minus I beta dx. So again, yji times dxi, well, they're both plus or minus 1. This expression is minus 1 if it's correctly classified, and otherwise it's minus. It's minus 1 if it's correctly classified, and plus 1 if it's. So it's a little complicated because there's a minus in front of it, right? So that means it's minus 1 if it's correctly classified, and plus 1 if it's incorrectly classified. So we get that the new weight, given the fact that this is just this whole thing is just plus or minus beta. So the new weight is x or minus beta if we're correctly classified, and the if it's incorrectly classified, then we are multiplying by x or plus beta. And we're going to write this in this way here: x wi times x of 2 beta times x of minus beta. And the reason I'm going to do this is because now I have the same factor here. I have an x of minus beta here. And if you remember what the error was, right, there was a sum over the wi's where it's misclassified. Divided by the sum of all the wi's. Well, you can see that it doesn't matter if I multiply all the weights by a common factor, because they're just going to cancel out in this expression here. So that means I can I get my update equation for the weights. If G classifies correctly, the weight